Alright, welcome to another lesson. Today, this is obviously a Unit 1 lesson where we have been talking about Newton's laws for over the past few lessons. Now, today we want to kind of utilize Newton's law and, of course, speak on the aspect of upthrust. All right, that's a very important topic here. And seeing that we're dealing with forces, right? Because upthrust is obviously a force. At some point, we'll see how Newton's law come into play as we talk about objects moving through fluids and so forth like that. So to begin, we want to look at what upthrust really is, right? I mean, I think you guys have heard about the term upthrust before. Now, another word that we can use to represent upthrust, we can say the buoyancy force, right? That's like the next word. If you end up seeing buoyancy force, it's the same thing as upthrust. Now, upthrust is related to the difference in pressure, right? At the top and the bottom of a fluid that is submerged in some type of liquid. Now, I know you might be wondering what exactly does that really mean. Now, let's imagine that we have a container with some fluid inside of it. It could be water, it could be oil, any fluid, so to speak. Now, remember that when you have fluid in a liquid, there is pressure inside of the container, right? And so if we were to put an object inside of that fluid, right? If the object is whether if the object is partially or fully submerged, there's going to be a force, an upward force, right? That will tend to push the object away. So imagine that you put an object inside of the fluid, right? The fluid is going to exert a force, and that force is as a result of a pressure difference. So the further down you go in the fluid, it's the more pressure that will be exerted, right? So let's imagine if we look at this example here. Give me a second, because I want you to understand exactly what we're saying here, right? So imagine that we have this um, uh, container with fluid inside of it, right? At this point, there is no object placed in the fluid. The only time we will have an upthrust is when there is an object inside of the fluid, right? Now that object can either be partially or fully submerged in the fluid. For this example, we will consider that the object is partially submerged. Now, if the object is partially submerged, right, from the top of the fluid, right, to the bottom of the object, here we have a height difference, so to speak. So at this point, we can almost calculate the pressure that would be exerted on that object inside of the fluid. Follow me? Right? So from this, we are having a pressure difference at this point because the object here is being submerged in the fluid, right? So that height difference will allow us to find the pressure, right? If the object was completely submerged, and you will see it in another example, if the object is completely submerged, right, then what we would do is find the total well, not the total, would find the difference in the pressure at the top of the surface and at the bottom of the object. So we'll have two difference in height, two height difference, right? And for that we can find what the pressure difference is. When we talk about upthrust, I'll explain this a little bit more in subsequent slides. But as regards to pressure, right? Whenever an object is placed inside of a fluid, according to Archimedes' principle, he was able to tell us that the upthrust on an object is equal to the weight of the fluid that is displaced. So can you imagine, by putting an object inside of a container, you would observe that the liquid or the fluid rises. So that increase in volume, so to speak, tells us that whatsoever volume that is displaced, right, if we were to take the weight of that volume of water that was displaced, it would ultimately tell us the upthrust of the fluid, right? So whatsoever the weight of the fluid is, it will tell us what the upthrust force is, all right? Because as the object moves in the fluid, right, it is displacing the water, and whatsoever amount of water or fluid that is displaced, the weight of that will tell us what the upthrust force is, all right? And it is, and there are many other ways we can look at it, right? So if the upthrust, in this case I'm going to use U for upthrust, if U is equal to the weight of the fluid, right, we can find the weight of the fluid using several things here, right? Firstly, we can say weight is equal to mass times gravity. But as it relates to the fluid, right, because the fluid has a density, follow me? So let's look at this now. So recall that density is equal to mass divided by volume. So to find the mass of the fluid, we will multiply the volume by the density of the fluid, which that is equal to the mass. So what we could do is say that our upthrust U is equal to, wherever we see mass, we're going to substitute that for volume times density of the fluid. So volume times the density times gravity tells us what the upthrust is, based on the fact that we know that weight has to do with mass times gravity, right? And in order for us to find that weight in terms of the upthrust, we would have to take into consideration what the mass really is, right? And from that, we know that the mass is equal to volume times density times gravity constant. So this tells us what the upthrust force is when we're considering it from Archimedes' principle. All right. So Archimedes' principle states that the upthrust on a fluid is equal to the weight of the fluid that is displaced. Follow me? All right, good. Now, we want to take the narrative from or want to take the concept of upthrust from pressure now. So we have found out that that our upthrust can be determined from the weight of the fluid displaced, right? We just found that out a while ago. Let us consider a cube placed in a container of water, right? Now, from the very moment we have a cuboid rather, placed in some type of container with water, we can expect that the fluid is going to exert a force in all, it's going to exert a force perpendicular to all the surface area. And I can show you from this angle. So this is what it looks like. So here we have the container. So this is a big container, all right? And we have water in it. Good. Now the cuboid has 6 faces, 6 equal faces. Now, based on what we're saying here, pressure is going to be perpendicular to all of the faces, right? Now, it's important to note that pressure is height related. When we look at the formula for pressure, you'll realize. Now, at this end, right, the pressure at that end is equal to the pressure at this end. The pressure at this side is the same pressure at the other side. So all those side areas, right, will have the same pressure because of the fact that pressure is height related. Those sides, the height is not being changed, right? So that's the reason why the pressure at those points are equal. So in a sense, if they are equal and opposite, then they're going to cancel out each other. Follow me? Right? So there's no, so overall, yes, there are pressures attacking each sides, but when you look at it, because all of those pressures are equal and they are opposite, they're going to cancel out each other. Now the difference now is at the top and at the bottom of the cuboid. At the bottom, right, there's going to be a much higher pressure, right, than at the top of the cube. Because we said that pressure is height related, then that's the reason why we can say this. Now, I think from fifth form, you would have probably done a few experiments when you had a container with fluid inside of it, and you probably bore a hole at the bottom and one in the middle and one at the extreme top. You would have realized that the pressure at the bottom, the spout would have been that water coming out would have had a much longer distance in terms of where it's coming out through, right? So that explains to us that at the bottom of a fluid or of a container with liquid or fluid, then the pressure is greatest at the bottom, and that is just because of the fact that pressure is height related. Now, yes, so since we can recall that pressure is equal to height times density of the fluid times gravity, right, we can derive an equation for the weight of the fluid. Now, we know that the weight of the fluid is equal to mass of the fluid times gravity. We said that already. Good. And we went ahead a while ago and derived a formula for the weight of the fluid. So at the end of the day, the weight of a fluid is equal to the volume of the fluid times the density of the fluid times gravity. But because we are dealing with volume, right? Volume speaks to height times area. Because of the container, the nature of the container that we're using, it obviously has an area and it has a height. We can replace the volume of the fluid right, with this formula to say that volume is equal to height times area times, well, yeah, the weight of the fluid is equal to height times the area, right, times the density of the fluid times gravity. But since we can also recall, so there are many things that we're recalling here. So we have now come up with a formula for the weight, and we know that pressure is equal to force divided by area. This is what we're doing here, is really deriving the pressure formula. So you might be wondering, what are we really doing? What we're really trying to do here is to derive the pressure formula. So if you were ever given a scenario where you need to derive how do we get that pressure is equal to height times density times gravity, this is where it is coming from. So let me just recap it now. So here we know that pressure is equal to force divided by area. Now the pressure that we're dealing with is as a result of the fluid that is displaced, right? So whatsoever amount of fluid is displaced, it is displaced based on the weight of the fluid that is displaced. All right. So that's a connection that I want you to get, that the pressure that we're experiencing has to do with the weight of the fluid that is displaced. And for that reason, that force that we're talking about is going to equal to what we just looked at right here. So that force that we're talking about is the actual weight of the fluid, right? And with that being said, we know that the weight of the fluid is equal to height times the area times density, right, times gravity, and all of that is divided by area. So we can see that area and area cancels out. So H times density times G gives us pressure, right? And this is just as a result of an object being submerged in a fluid. Because the object is being submerged in a fluid, it's going to experience a pressure. Now that pressure is amount to the force that is that the object has, right? And that force that we're really talking about is equivalent to the weight of the fluid that is displaced, right? Which is ultimately the upthrust force. Because remember, we said that upthrust is related to pressure differences. So that's how we would have gotten this equation that say that pressure is equal to height times density times gravity. Now, with that being said, right, we can, according to the Pascal principles, there are a few things that Pascal principle tells us, and I think I looked at it already when I was looking at this diagram. It tells us that the pressure of the fluid acts equally in all direction, right? And when we talk about all direction, we're talking about the sides, so to speak. Yeah, and it acts perpendicular to any surfaces, so it will always form a right angle between the surfaces. Now, seeing that we can, how would I say it? From the fact that we know that pressure is equal to force divided by area, we can make a transposition using that same formula. So if pressure is equal to force divided by area, we can then find what the force is. So the force that we're considering here is really equal to force is equal to pressure times area. Good. So that's just a simple transposition here. This force that we're trying to find here is the force that will be experienced at each faces at the top and at the bottom respectively. All right, so because there is a different pressure at the top and there's a different pressure at the bottom, we can expect that there's a different force and at the bottom and at the top. So this is when the object is completely submerged. So once it is completely submerged, then we expect that the pressure at the top is going to be different. Hence, there's going to be a different force at the top, right? And there's going to be a different force at the bottom. So with that being said, we can write this equation here to say that force 1 is equal to pressure 1 times the area. And we know that that the pressure at the top is height related. So whatsoever the height at the top of the fluid is to the face of the top of the plate, right? We can write that to say that height 1 times the density of the fluid times gravity times the area will tell us what that force is. And for force 2, we'll do the same thing, but the height is from the top of the fluid to where the bottom plate now starts. You understand? So with that being said, since the heights are different, meaning that height 2 is much larger than height 1, we can then find the net force in the vertical position, right? And not only that, because the pressure, right, at the bottom is much greater, then we can now see that because of that pressure difference, the object will move upwards because F2 is of a larger magnitude in terms of force, and as a result of that, it would tend to push the object up in the air. You understand? Because the pressure at the bottom of the fluid is much greater than what is at the top. And with this being said, we can find the overall pressure, which is just subtracting the forces that is experienced at the bottom and at the top. Force at the bottom is F2 and force at the top is F1. This mathematics will just tell us that the overall pressure, and the overall upthrust is equal to height 2 minus height 1 times the density times gravity times the area. This is just telling us the upthrust of the fluid. Since upthrust is pressure related, right? Then because of the nature of the fluid is going to experience a different pressure at the top. So there's a different upthrust at the top and there's a different upthrust at the bottom. So in order to put everything together, we had to go through this procedure. All right. Now, important point to note is that if the weight of the cuboid is less than the upthrust, then according to Newton's second law, we can expect that the cuboid will accelerate upwards. So let's imagine now that after working out the upthrust and then calculating the weight of the cuboid, I will realize that the weight of the cuboid is less than the upthrust. It then tells us that the object will move upwards, and because it's moving, we can then link Newton's second law to say that the net force is equal to mass times acceleration. So if you were ever given a scenario where you need to determine the acceleration of the cube, you know, when the weight of the cuboid is less than the upthrust, then this is what you would ultimately have to do, right? So because we know that U, which is the upthrust, minus the weight, right? We would just use this equation right here, you know, because going back to this, we realize that the weight of the fluid is going to be acting upwards, and well, the pressure, the fluid rather, is going to exert that force one upwards, and then now force one coming down is going to be the actual weight of the cuboid, right? Because it's that weight that is going to cause that weight of the fluid, that weight of the object rather, is what would result into the weight of the fluid displaced, right? So this is what we end up with if we want to try to find that. So yeah, height 2 minus height 1 times the density of the fluid times gravity times the area is equal to mass times acceleration. Now moving along a little bit, so we have talked about upthrust, and now we want to shift our focus a little bit to what we call resistive forces in a fluid. Now, whenever an object is moving in some type of fluid, there's going to be some resistive force, right? And that type of resistive force in a fluid or in air, we refer to it as a viscous drag, right? Or we can call it a drag force, right? Yes. So once it's moving through some type of liquid or possibly through air, we refer to that frictional force as the drag force or the viscous drag. And you can read the first point here. It says that when there is a relative motion between a fluid and a solid, right, forces of friction arises within the layers or within the liquid of layers of fluid sliding across each other, right? Now, whenever we're talking about this type of thing, we will come across a thing what we call the coefficient of viscosity, right? And here there's a symbol for viscosity. It's like an N but with a much extended length of one of its sides. So viscosity is given by this symbol right here, and it is measured using kilograms, meter, uh, kilogram. Yeah, I always have some issues saying this. So kilograms, meter to the minus 2, or we could say kilograms per meter square times second. This is the unit for the viscous drag, or we can say that's pressure times the time, right? Now, they're saying now the greater the viscosity is, it's the greater the viscous drag, which tells us that the greater the frictional force would be. So, viscosity has to do with a measure of a fluid resistance to flow. Now, different fluids have different resistive ability to flow, meaning that it is all dependent on what is used to make up the liquid. We can compare this in terms of honey. Like if you look at honey is going to be more viscous than water. You understand? Because of the nature of what honey is made up of, those different types of bonds and so forth. Honey is very thick. So for that reason, we say it is more viscous. And yeah. And if we want to measure the viscosity of that, then, it's going to take us into some whole heap of craziness. All right. But yeah, so now let's imagine that we can try to find the viscous drag force, right? At on a sphere at low speed, right? And whenever we're thinking about a sphere at low speed, we will utilize what we call Stokes' law, right? In order for us to find out what the drag force really is. Now, in order for us to do this, imagine that you have some object um, in well, a sphere rather, in some viscous fluid, right? We can say now that there are several forces acting. One of the force is that is acting here is the weight of the object that is acting directly downwards. Now we know that there is going to be an upthrust force due to the fact that once we have some object inside of some fluid, upthrust is going to come arise. Now, because the object is moving down, right, then there's going to be a drag force which is equivalent to this. This is when the system is at low speed. So the drag force is equal to 2 pi times the coefficient of viscosity times r, which is the radius of the sphere, times the velocity at which the object is moving. And that velocity, you're going to hear us talking about what we call terminal velocity, right? And in a nutshell, terminal velocity is a velocity that is obtained while the object is moving through the fluid. All right, we'll talk about that a little bit more, but I want you to pay attention to this now, because we know that force, the weight of the fluid, not the weight of the fluid, the weight of the object is equal to mass times gravity. But by way of trying to find the mass of the sphere, we can use the fact that if we know the volume and if we know the density of a sphere, we can ultimately find the mass. So let's recall that mass is equal to volume times density. And if we're trying to find the density, or if you're trying to find the mass as it relates to the object, we can, because it's a sphere, as the volume of a sphere is 4 divided by 3 pi r cube. And if we know the density of that object, we can ultimately find the mass. So that's the reason why we have this right here. Right? That's the reason why we have this, because we just replace mass with volume times density. Similarly, because we know that whenever we're dealing with upthrust force, right, we can say that the upthrust force or the buoyancy force is equal to the weight of the fluid displaced. Good? Now, in this event, right, we can, because we're dealing with a cylinder right here, the volume of that is equal to this, right? 4 divided by 2 times r, 4 divided by 3, I should say, pi r cube. But in this event, we are considering the density as the density of the fluid. Okay, so that's something that you have to pay attention to, that it's the density of the fluid that comes into play at that point whenever you're trying to find that buoyancy force that the fluid will, yeah. Now imagine if the object was at high speed. So if the sphere was moving through the fluid at great speed, right, then we would consider the frictional drag force as d times the area times the density times v squared, right, where d is just a drag coefficient, right? The A is the area of the sphere, right? And we know that rho is the density and v is just that velocity, the object's velocity. Now, Stokes' law is this equation right here. It says that the frictional drag force is equal to 6 pi times that coefficient of that viscous drag, I should say, right, times the radius times the velocity. So that's what Stokes' law is in a sense, and it has to do with the frictional drag force when the object is moving at slow speed, or very low speed, I should say. It's not moving fast, and this is just due to the viscosity of the fluid. So as it relates to terminal velocity, right, when an object is falling through a viscous fluid, right, we know because the object is moving, there's going to be a point where once the object starts to move through the fluid, whenever the the upward force is equal to the downward force, we say that the object is at terminal velocity. And once that happens, it tells us that the net force on the object is equal to 0, which means that there's no acceleration at that very point, because acceleration has to do with change in velocity. So remember that acceleration has to do with the rate of change in velocity, right? So if when the object has reached a point of balance, where the upward force is equal to the sum of the upward force is equal to the downward force, right, then it tells us that there won't be an acceleration, because we have reached a point where we call terminal velocity, and that is just when the upward force is equal to the downward force. So in essence, we're saying that at terminal velocity, this is what it equals to: the net force. So for the upward force, we know that the upward force is the upthrust force, right, plus the frictional drag force. So that's our upward force. So by way of finding the net force, this upward force, obviously we can just say it's the larger force for now, because it's going, well, not say it's the larger force, because it's going up, we write it first, minus the weight, which is Fg. Now this is it, by way of looking at Newton's second law, is equal to mass times acceleration. We have come to a point where we say that because whenever the object has reached terminal velocity, right, then the velocity is going to be relatively constant. So if the velocity is constant, then there is no change in velocity, and once there is no change in velocity, then there's no acceleration, because acceleration has to do with change in velocity. So it boils down to the fact that Fb plus Fd minus Fg is equal to 0. Good? And with that being said, we can now say that the upward forces, the sum of the upward forces is equal to the downward force. Good? So whatsoever the upward forces are, we can now say that it is equal to the downward force. Alright? So if you know the downward force, you can ultimately know the upward force, the sum of the upward forces, and so on. Now, quite often you will be required to find the terminal velocity. Good? So quite from time to time you will be asked to find that. From a graphical standpoint, right? This is what it looks like. So as velocity changes with time, remember the very moment you put the object in the fluid, right? The velocity will change, but as soon as the upward forces is now equal to the downward force, then we reach to a state we call terminal velocity, right? And at terminal velocity, the velocity remains constant throughout the entire duration, so to speak. Now, that's that's not it. That's it as it relates to terminal velocity. So we have covered terminal velocity and what it really is. Now, let's just talk about a little bit about static and dynamic equilibrium. Now, here we have a thing what we call translational equilibrium, and it says that translational equilibrium occurs when the net force on an object is equal to 0. By Newton's second law, the object, the acceleration of the object is 0. So if you think about an object sitting on a surface that is not accelerating, right? The net force is equal to 0, which tells us that it is not accelerating, and as a result of that, we refer to that as what we call stationary equilibrium. And you know that equilibrium has to do with a state of balance. So that is just what static equilibrium really is, right? And it's just when an object is stationary. Now, as soon as an object is moving at a constant velocity, right, such as terminal velocity in that sense, we now have a state of what we call dynamic equilibrium, right? And that can be observed when we look at the scenario just now with the fluid, the object moving in a fluid, right? And once it has obtained that terminal velocity where the upward force is equal to the downward force, right? Then we can say that we have what we call dynamic equilibrium. And it is just as a result of the fact that the acceleration is constant. Even though it is moving, right, it won't have a change in acceleration, right? Or well, it won't have an acceleration because of the constant velocity that it has. Good. So that's what these equilibrium speak to. So translational equilibrium is just when the net force is equal to 0, and all it's really telling us is that the acceleration is equal to 0. Follow me? So once the acceleration is equal to 0, you can have acceleration equal to 0 in two scenarios. Either the object is not moving, and at that point it's at static equilibrium, or if you have constant velocity. So if you have constant velocity, then you won't have a change in you won't have an acceleration. So for that case, we refer to that as dynamic equilibrium, right? So that's what translational equilibrium speaks to, right? And it's just when, as I said before, when the net force on, of an object is equal to 0. Now there's another type of equilibrium. So we have translational equilibrium, right? But now we have rotational equilibrium. And we generally observe this type of equilibrium when we have the concept of moments, right? Now moments is what we call a turning force, right? Or yeah, moment is as a result of the it's really as a result of some turning effect of a force. So typically, if you have a seesaw, right, and it is pivoted at some point, now depending on where the forces are located, right, then those forces will cause a turning effect, so to speak. Good. Now from the whole aspect of moments, we can say that F1 is going to cause an anti-clockwise turning effect, which therefore tells us that if you're looking at anti-clockwise, then this is the direction that it will move in, right? Because clockwise moves from right to left. Anti-clockwise then moves from left to right. Good. Now, as it relates to F3, F3 will cause a clockwise force, right? Now this is where F2 is. F2 is at the pivot point. Because F2 is at the pivot point, then it will cause no turning effect at that very point. F3 would cause the clockwise turn. So clockwise is related to F3, and F1 is associated with anti-clockwise. Good. Now moments is just simply what we refer to as the torque, right? And this is calculated based on the force times the perpendicular distance away from the pivot, right? So that distance that is from the pivot that is perpendicular to the force, which means that it must forms a right angle between the two of them, we can then find what the moment is. Now we can put things together to say that whenever we're talking about clockwise torque, we can designate clockwise to be positives and anti-clockwise torque as negative. All right. Now, in essence, if we can go ahead and find the net torque that is associated with this scenario here, right? By net torque, we're just adding up the torques, so to speak. So we know that F3 is, because it's clockwise, it's going to be positive. F2, because it's at the pivot point, there is no perpendicular distance, then that is equal to 0 minus the moment caused by F1, which is, because it's anti-clockwise, we say that it's going to equal to you're going to use a negative, right? So with all of this, if there's a scenario, so this is just finding the net torque, right? But now it says no, when the net torque is equal to 0, right? It tells us that the beam is stationary. So if you realize that after adding and subtracting these moments, if the net torque is equal to 0, right, then it tells us that the thing is stationary. So at that point, we have what we call static rotational equilibrium. You understand? Because it's not moving, but we're dealing with a rotational equilibrium. So we refer to it as static rotational equilibrium. But now, in the event that there's some amount of, well, yeah, if the net torque or the net moment is not equal to zero, then we then say that we have what we call dynamic rotational equilibrium. Follow me? So rotational equilibrium can be classified as static rotational equilibrium and dynamic rotational equilibrium. Now, static rotational equilibrium is when the net torque is equal to zero, right? And dynamic equilibrium is as a result when there is some rotation at a constant frequency at, about at the pivot, and which is just tell us that the okay. Well, okay, I see. So it's so yeah. So dynamic rotational equilibrium is still when the net torque is equal to zero, but there is a rotation at the pivot at a constant frequency. All right. So I believe that's about it that we need to cover. All right. So if there are any questions, feel free to you know, or any concerns, feel free to point those out to me, right? Yeah.